Hello students, this is Professor Chalai, and in this video we're going to look at standard enthalpies of formation. By the end of this video, you should be able to define the standard enthalpy of formation, you should be able to balance standard enthalpy of formation reactions, and you should be able to use the standard enthalpy of formation to find standard enthalpy of reactions. Let's get started. As always, you can follow along with our Chapter 5 workbook. So what is the standard enthalpy of formation? Well, right away you should be thinking that it's an enthalpy for some type of reaction, that it occurs in a standard state because there's a degree symbol. So let's look at exactly what it is. The standard enthalpy of formation is the enthalpy for a reaction where exactly 1 mole of product is formed from its constituent elements in their most stable states under standard conditions. And so because it's an enthalpy for 1 mole of product, the units will be in kilojoules per 1 mole of product. Okay, what does that even mean? Well, let's look at the standard enthalpy of formation of something like carbon monoxide gas, right? That's the product that we're interested in, so the enthalpy for this reaction will be the standard enthalpy of formation. We need to form carbon monoxide from its constituent elements in their most stable states under standard conditions. So the constituent element is carbon and oxygen. So carbon in most stable state is going to be in the form of graphene, right? So solid graphene. And oxygen, the most stable state of oxygen under standard condition is actually oxygen gas. So O2. So to make this equation balanced to form 1 mole of product, we actually need to balance this with fractional numbers. So we have half oxygen. So 1 carbon from graphene, or graphite actually, and half of an oxygen gas molecule will give us carbon monoxide gas. And so the enthalpy for this reaction is the standard enthalpy formation of carbon monoxide. What this means is that if you already have something that's in their most stable state, let's say you're looking at oxygen gas, to form oxygen gas from oxygen atoms in their most stable condition, it'll just be from oxygen gas. So the standard enthalpy of formation for this is going to be 0 because no reaction is actually happening there. Okay, so this table just lists a bunch of standard enthalpies of formation under standard conditions at 25 degrees Celsius for a lot of different compounds. And so you'll see, for example, bromine to liquid is 0. That's because that's the most stable state of bromine in that condition. Calcium is a metal, and usually for metal, it's just going to be a single atom solid, and that's going to be the most stable state. Here it is for carbon. The solid form of carbon, graphite, is the most stable state, and then there's a whole list of different carbon compounds listing their standard enthalpy of formation. If a value is not on this table, you would have to look that up online. Okay, let's use these. Let's use standard enthalpy of formation to figure out the equations associated with them. So number 27 says write a balanced chemical equation for the formation of 1 mole of each of the following compounds from their respective elements in their standard states. So I'll do the first one for you for practice, and then you can try the others. Let's look at magnesium carbonate. So magnesium carbonate solid. And let's see how it's formed from its constituent elements in their standard states. So magnesium is a metal, so I don't even have to look at the table. I know magnesium exists as magnesium solid, just one atom. And to balance that out, we just need one of that to balance the one magnesium there. Carbon, as we mentioned before, exists as carbon solid in the graphite form. So I'll just put graphite there so we know what it is. There's one carbon there, so I don't need anything else to balance that out. And then oxygen, we know exists as O2 gas in the standard state, most stable form. We need 3 oxygens. We have 2. We can't change the number of moles on the product side. So to balance this out, let's put 3 over 2 moles of oxygen. So 3 over 2 times 2 will give us 3 oxygen molecules, or 3 moles of oxygen. All right, try B, C, and D. If you're not sure what the standard state of any element is, you can look at the table here. The ones with 0 correspond to the most standard states for those elements. And if it's a metal, just know that metal exists in their elemental form as a solid. That's already their most standard state. When you're done, unpause the video and I'll go over them with you. Okay, let's look at B. That's C6H12O6, glucose, solid. Carbon, we already mentioned, carbon exists as graphite. And there's 6 carbons here, so let's make that 6. Hydrogen, if we look at our table above, we see that for hydrogen, the most stable state for hydrogen is H2 gas, hydrogen gas. So we'll use H2 gas. There's 12 of hydrogen on the right. We need 12 on the left, so let's make this a 6. And then finally, oxygen, we know that exists as O2 gas. We need 6, so let's multiply that by 3. Okay, let's look at NaCl. NaCl, solid. Sodium, right, is a metal, exists as sodium solid. Chlorine, according to the table, exists as chlorine gas. So we need half of 1 mole of chlorine gas to make 1 atom of chlorine and sodium chloride. And then finally, lead nitrate or lead 2 nitrate. We have PbNO3 2 solid. Lead is a metal. There's only 1 of them, right? So we just need 1 of those. Nitrogen, there's 2 nitrogen, most stable state is nitrogen gas, and there's 2 atoms of nitrogen on the right, so we just need 1 mole of nitrogen gas on the left. And then oxygen, there's 3 times 2, 6 oxygen. We know oxygen comes from oxygen gas, O2. And then to get 6 oxygen atoms, we'll need to multiply this by 3, and so that becomes balanced. Okay, I hope that all makes sense. We're just breaking them down into their atomic components and figuring out which one, what are their most stable forms in order to write this reaction. So the delta H for each of these reactions will actually be the standard enthalpy of formation. So you might be asking, why is finding standard enthalpy of formation useful? And that's because we can find the enthalpy of the entire reaction just by adding up the enthalpies of formation. So if you want the enthalpy of a reaction, or the standard enthalpy of the reaction, you add up all of the enthalpy of formation for the products, multiply by the number of moles, subtract the number, the enthalpy of formation of the reactants, multiply by their number of moles. So I'll do 28A for practice, and I'll show you how this works. Okay, let's look at 28A. We have this reaction, and the question is, what is the enthalpy, standard enthalpy of this reaction? My pen doesn't want to work. There we go. What is the standard enthalpy of this reaction? Well, we should use standard enthalpy of formations to find it. All right, so on our reactant side, we have ammonia gas and oxygen gas. The standard enthalpy formation of ammonia, if we scroll all the way up, ammonia is right here. It's minus 45.9 kilojoules per mole, right? The units of kilojoules per mole. So I will write here minus 45.9 kilojoules per mole. It's times 4 moles of ammonia gas. For oxygen gas, we know the enthalpy of formation of oxygen gas is 0 because it's already in the standard state. All right, On the product side, we have 4 moles of nitrogen monoxide gas, and the standard enthalpy of nitrogen monoxide gas is 91.3 kilojoules per mole. So that's right, 91.3 kilojoules per mole. As you can already see, the moles will cancel out in each of these to give us just kilojoules. And then for water gas, so water vapor, if you look on the table, we'll have 6 moles multiplied by negative 241.8 kilojoules per mole. Okay, so the equation says that the standard enthalpy of the reaction is all of the products subtracting all of the reactants. So the standard enthalpy, there we go. Standard enthalpy for this reaction is going to be all of the products. So 4 times 91.3 kilojoules per mole plus 6 times negative 241.8 kilojoules per mole. Keep in mind the negative signs, right? And then you're subtracting 4 times negative 45.9 kilojoules per mole. So you punch all of that in your calculator, and let me just write it down so that we see everything. So it's 4 times 91.3 plus 6 times negative 241.8 minus 4 times minus 45.9, all of these in kilojoules, right, because the moles cancel out, and you should get minus 902.0 to 1 decimal place, because these are all adding or subtracting kilojoules. So the delta H for this reaction is minus 902.0 kilojoules. Okay, try part B by yourself. Note that for some of these, you will have to look up the standard enthalpy of reaction online because I don't have them on the table. I just want you to get in the practice of trying to look for these values wherever you can find them. Excuse me. Okay, so let's look at this. We know that aluminum is a metal and it's already in a solid form, so that will have a standard enthalpy of formation of 0. Iron 3 oxide, if you look this up online, you'll find that it has a standard enthalpy of formation of negative 824.2 kilojoules per mole times 1 mole. And then on the product side, aluminum oxide has a standard enthalpy formation of minus 1676.7 kilojoules per mole times 1 mole. And iron is a metal in a solid form, so that's already 0. So if we're calculating the standard enthalpy for this reaction from standard enthalpy of formation, it will be negative 1676.7 kilojoules minus negative 824.2 kilojoules, and that will give us negative 852.5 kilojoules. Remember that standard enthalpy of reactions, if it's negative, it's an exothermic reaction. If it's positive, it's an endothermic reaction. All right, so that's how we can calculate the standard enthalpy of reactions from standard enthalpy of formation. How do we put all of this together in a single complicated question using all of the things that we've learned so far in this chapter? Try number 25 on your own. You will have to look up the standard enthalpy of formation of octane online because it's not in the table, and try to calculate the amount of kilograms of octane necessary to burn to get the amount of energy per day in Indiana. Pause the video here, try to work this one out, struggle with it, and then we'll go over it together afterwards. Okay. Before we can get the standard enthalpy of reaction, we need to actually write some sort of reaction to work with. So we know this is a combustion reaction that's burning liquid octane. So we know we have C8H18 liquid. We know that combustion is reacting with oxygen gas to form carbon dioxide, CO2 gas, plus water vapor, H2O gas. And so we want to first find the delta H for this reaction under standard conditions using standard enthalpies of formation. So let's first balance this equation. We have 8 carbons on the left. We have 1 on the right, so let's make that 8. And I will use a different color to balance it. There we go. 8. We have 18 hydrogens on the left, 2 on the right. So if we multiply that by 9, we'll get 18. Now let's look at our oxygens. We have 8 times 2, that's 16, plus 9, that's 25. Yeah, that's 25. We have 2 on the right. So if I do 25 over 2, that will be balanced. Now, remember, for standard enthalpies of reaction, we could have fractional numbers in the balancing of the equation. So I could stop here, or you could balance it with just all whole numbers. Either way, your final answer should come out to be exactly the same. If you want, you could try it both ways. But let's work with it here, because this is not the final answer. We just need this to find the final answer. So I'll stop here and not put any more effort into balancing this. Okay, but all the elements should be balanced. We just have fractional numbers, and that's okay. So let's see if we can use standard enthalpy of formation to find the standard enthalpy of this reaction. If we looked up online, we'll find that the standard enthalpy of formation for liquid octane is negative 249.7 kilojoules per mole multiplied by 1 mole. We know that the standard enthalpy of formation of oxygen gas is 0 because that's already in the most stable state and it's an elemental form. In the table above, we see that the standard enthalpy formation of carbon dioxide gas is minus 241.8 kilojoules per mole times 8 moles. And then we have water vapor, H2O gas, and so that is from the table minus 39, sorry, I mix these numbers up. This is minus 241.8 kilojoules per mole times 9 moles. And this is minus 393.5 kilojoules per mole. Okay, so if we add all of these up, then the standard enthalpy of this reaction will be minus 393.5 times 8 plus minus 241.8 times 9 minus 249.7. And so this all comes out to negative 5074.5 kilojoules. So that's the standard enthalpy of this reaction, minus 5074.5 kilojoules. And this seems to make sense because it's negative. We know combustion reactions, it's producing heat, so it's an exothermic reaction. All right, so this is all good. However, the final part of the question asks us what amount of octane in kilograms is necessary to produce this amount of heat. So let's figure that out. We start with 1.1 times 10 to the 12 kilojoules of heat, right? We know this standard enthalpy of reaction is for this equation, which is for 1 mole of octane. So to convert this into moles of octane, right, we know that the equation produces 5074.5 kilojoules of energy for 1 mole of octane. So this will help us convert the total amount of energy that we started with to how much total amount of moles of octane that we needed to burn to get there. But we don't need moles of octane, we need it in terms of kilograms of octane. So we can convert moles of octane to mass by using the molar mass. The molar mass of octane, which I'm sure we can all figure out by now, is 114.23 grams per mole. So this would be times 114.23 grams per mole of octane. This will give us the answer in grams, but we want the answer in kilograms, and so we do 1,000 grams is 1 kilogram. Plug all of this into our calculator, and we should get to two significant figures, 2.5 by 10 to the 7 kilograms of octane. All right, so to go over, first we need to write a balanced chemical equation before we can write a standard enthalpy of reaction for that equation, simply because we can't have an enthalpy of reaction without a balanced equation. Second, we then looked up the values of the different enthalpies of formation for the different components of that reaction, add them all up to find the standard enthalpy of that reaction. Once we have that, we can use that to figure out how much moles we need to produce this amount of energy. Once we have number of moles, we can convert it to mass and then convert it to kilograms to get number of kilograms of octane. Okay, this brings us to the end of this lecture. In our next lecture, we're going to look at Hess's law, which is a lot of fun. We'll see you then. Bye.